Hey, welcome everyone. So today we'll be doing a final exam review for Math 134, Biocalculus. So what I've done is I went through each week and I selected one problem from each topic. So no final exam review is perfect covering every single thing, but I've done my best job to select some nice problems to discuss today. So the video recording will be posted online, and these solutions are also posted online on eClass. All right, so let's get right into it. So week one, we did some pre-calculus topics. So in this problem, we give you a function. There's our function right there. And we say to solve the inequality of f of x's absolute value less than a half. Okay, so if f of x is less than a half, or it's greater than minus a half, we'll satisfy those conditions. So there's a few ways that you can solve this problem, trying to solve that inequality. You could do it algebraically. You could do it graphically. I'm going to do it graphically. The algebraic method is for cowards. We can draw a beautiful graph today of what we have using our transformation of a graph that we know. So if we think about the graph of y equals 1 over x, that graph looks like this. And the only difference here is that it's been shifted up 1 unit. So the asymptote is instead at y equals 1. Okay, and we are looking for f of x values. So this vertical axis here is f of x. We want f of x values in between minus a half and a half. So let's try to search for those values. So 1/2 would be about right there. And minus a half would be about right there. So we want to know, well, what would this point right here be? So when you plug in one-half for, I guess, 1/2 for y, we should make sure that we're leaving some space for y here and x. So 1/2 is the y value, and we want to search out the x value. And then when the y value is minus 1/2, we want the same thing. We want to search out, well, what is that corresponding x value? So what we could do here is solve our equation that we're given for those corresponding values. So I'll do this quickly to make sure that we can get through all the topics today. So what I want is 1 over x plus 1 to either equal plus 1/2 or minus 1/2. So if you go ahead and solve that, what you're going to get is that x is equal to either minus 2 or minus 2/3. So those are the corresponding x and y values that we have come up with here. So the minus 2 would be the one that's further to the left. That would be minus 2, and then this one would be x is minus 2 over 3. And those would be the corresponding x values that would satisfy the inequality. So the answer would be x is an element of minus 2 going up to minus 2 over 3. And like I said, there's some other ways to solve it. You might want to look at the solutions on eClass for another method. Okay, so week 2. One of the things we talked about in week 2 was sequences. So here's a sequence, and it asks us if it's convergent or divergent. So that immediately makes me think of the limit. So we need to have the limit as n goes to infinity of this thing that they gave us, the sequence of numbers, b sub n. And now we'd like to know if it's convergent or divergent. So I have to go ahead and take that limit. So I have a limit as n goes to infinity. And the expression here is logarithmic. We have a log minus another log. So how about we combine that into one logarithmic expression? So we have 7 n to the power 4 plus n to the power 3 multiplied by 9, all divided by 2 n to the power 4. So we can go ahead and take the limit as n goes to infinity of the stuff inside of the log and see what happens there. And to do that, all we need to do is focus in on the coefficient of the largest power, which is 7 and 2. So that's what we get as our answer. We get ln of 7 over 2. Now, if this was going to plus infinity or minus infinity, then it would be divergent. But in this case, it's of course convergent because we got a specific number. So 7 over 2 is what it converges to. That is the limit, and it's convergent. So let's just be really clear, write down that answer. Okay, so that gives you a little bit of a review of sequences. What's next? So week 3, we talked about limits, asymptotes. So here's a limit problem that I think you'll find rather helpful to discuss. There's some practice on this one, and I think that some questions came up, so it's good to discuss this type of problem. So we have the limit as x approaches 3 of ln of the absolute value of x minus 3. So let's try to think about what happens inside of the absolute value. That's really always the key to the absolute value. So we're trying to plug in values of x that are close to 3. So it's going to be close to 0 when we're plugging in numbers here that are close to 3, like a 3.1 or a 2.9. And then we're taking the absolute value. So it's always going to be something close to 0, but we're only going to approach from positive values. So from there, you might be able to think about what the answer is. Maybe if we draw the function of y equal to ln x, our function looks like this. You might be able to think about what the answer is, but I'm going to give you a little bit of an algebraic approach this time. You could think about making u equal to the absolute value of x minus 3, just as one possible approach here. You can think about, okay, x is going to approach 3. And as x approaches 3, then something happens to u. It approaches 0, but only from the right-hand side, because we're taking the absolute value. So we can rewrite this limit with a u substitution so that we have u going to 0 from the right-hand side. And then everything that we have left over would be ln of u. So now if we view the ln function in this way, we're approaching 0 from the left-hand side, or from the right-hand side, going towards the left-hand side of our diagram. And then ln x approaches negative infinity when that happens. So we get a negative infinity as our answer here. Remember, you can say that such a limit does not exist, but when you know that you can describe it a little bit further as maybe plus or minus infinity, you should do that. That might come up on your final exam where you have a choice between the limit doesn't exist and the limit's infinity, and you should put an answer down as infinity because you're able to describe why it doesn't exist as a real number. Okay, so one of the things that we talked about in the next week was taking a derivative by definition. So of course, you won't have to do this full process when you're writing your stack exam, because it's more just about plugging in the answer, but you might have to still know, what this formula is and maybe how to apply it and what it actually means. And you might also think, well, there's just faster methods to take this derivative, and I can use those faster methods, but they all come from the definition. If we don't have the definition, we don't have those faster methods. So it's definitely something that you're going forward in calculus, we should know about. Okay, so reminding ourselves of the formula, it's the limit as h goes to 0 of f of x plus h. So I have to write down the function, and instead of writing x, I write x plus h. And then we subtract f of x, which is 1 plus x under the square root, and we divide everything by h. Okay, so from here, try to solve our limit. So here's another type of limit that might come up on your final exam. Remember, when you have square roots, you'd like to get rid of these square roots. The tool that we have to do that is multiply by the conjugate. So the conjugate is, rewrite everything that we have and change the sign. So instead of it being the difference of these square roots, we're adding the square roots. And we're going to do the same thing to the top and the bottom, so that we're keeping everything nice and balanced. Okay, so we have a limit as h goes to 0. So in the numerator, we got to use our difference of squares. So we can square and take the difference. So we have 1 minus x, or 1 plus x plus h minus 1 minus x. And that's all over h. And then the square root of everything that was left over, that mess. So square root 1 x plus h plus 1 plus x square root. Right, so the bottom had to keep that disaster, but the top really cleaned up nicely for us. So now we have a 1 minus a 1 and an x minus an x. So all that's left is an h on the top, and that h cancels out with what's on the bottom, the h that's there. And that's really the key to doing these types of limits. You need to make sure that h cancels out on the top and the bottom. And then from here, we can take our limit. We can plug in the 0 to the x value and get the result of our limit. So the numerator is just 1, and then we have 2 of the square root of 1 plus x in the denominator. And that becomes our answer. And you could also check by just taking the derivative here by the chain rule, and you'll find the same derivative. Yeah, so a question that came up privately in the chat just about the last problem, to revisit it for a moment. I changed a two-sided limit to a single-sided limit. And that really just happened because of the absolute value, right? The absolute value is making everything positive. So we're approaching things from the right-hand side after I make that u substitution. So that's why I didn't have to consider the two-sided limit, because the u is being represented as the absolute value of x minus 3. Maybe so one more thought, you could think about, if you wanted to draw ln of the absolute value of x, that function would look like this. And you could then think about the two-sided limit at 0 if you wanted, right? There's a two-sided limit, and from both sides, it goes to negative infinity. So that would be one way you could consider a two-sided approach if you wanted to look at that diagram instead. Do I have a general rule for getting rid of h? Well, you have to manipulate the numerator somehow so that you have a factor of h. So how is that manipulation done? It does depend on the problem a little bit. It could be that you have to just factor until you factor out an h. You could have to do what we did here, multiply by the conjugate. But regardless, after you factor it completely and you cross out any like terms like we did on this stage, the general rule would be that you must have a factor of h to cross out on the top and bottom. If you don't have a factor of h at this step on the top and bottom, something's gone wrong. Okay, so after we did the definition, we got all kinds of different rules about taking derivatives. We could use these rules to really speed up the process. So in week 5, I called it advanced differentiation rules. So we're going to look at an example where we can quickly take the derivative. And one thing that I want to remind you of, if you have a problem like this, don't simplify your derivative really before or after. Just take the derivative, type it into stack, and move on to the next problem. You don't have to massage it down to anything really nice. If it's big and ugly, that's fine. Okay, so what do we have to do here? First, it's a quotient rule. So maybe we'll just write out the structure of our quotient rule. We have something minus something in the numerator, and then the denominator will get squared, so it'll be tan to the power 4. Now we just have to sort out what the numerator is. So in the numerator, first we have to deal with the derivative of the top part. So we have an exponential function, so we rewrite the exponential, so e to the x sine x, and then we take the derivative by the chain rule of the power that we just copied. So we have to take the derivative of x, which is 1, copy the sine x, and then plus copy the x, and then the derivative of sine is cos. Okay, so then multiply by the denominator, right? The plus 10, its derivative is 0, so that part goes away. You could write plus 0 if you like, but I'm going to run out of space if I do that. So multiply by the denominator, which is tan squared. The bottom gets multiplied, and then we do it the other way around, right? We copy the numerator, so e to the x sine x plus 10. This time we do have to have the plus 10 because we're doing a copying stage, not a derivative stage. And then we take the derivative of tan squared. So pull down the 2, copy the tan, drop the power to 1, so it's tan to the power 1, so just leave it just like that. And then multiply by the derivative of tan, which is secant squared. And that's it. That's the whole show. As I said, we don't want to do anything fancy with this. Just leave it like this and type it into stack, move on to the next problem. All right, on to week 6 concepts. So in week 6, we did some applications of derivatives. And one of the things that we did was a method of linear approximation. So you may have to do this on a final exam. Let's remind ourselves how this works. So first we take a graph, and our particular graph is the square root function, which looks like this, except we've shifted 1 unit to the right. So our square root function is that. So we have f of x is equal to the square root of 1 plus x. Okay, now it's saying we're supposed to do some approximation at a equals to 0. So we're going to approximate using this point right here, a equal to 0, a point on the x-axis. And we're going to use that point to come up with a tangent line. And the idea is that that tangent line, we'll call it L of x, is going to help us estimate what's going on with our curve. So we're going to be able to estimate the square root of 1 plus or 1.06 underneath the square root. And we're going to be able to do this with just our bare hands. Okay, so we need to identify what this line is. So the line has a slope, and the slope is given to us by the derivative. And then a point that's on our line would be, this point right here. If I draw it in right there, that point is A, comma f of A. So for whatever problem you do, you'll have that point available to us. So we can use the point slope form of a line to write down the equation of the line. Okay, so there's my line. Now to finish off the job, we have to, of course, plug in A, and we need to know what the derivative is. So let's go ahead and take the derivative. So my f prime of x, we bring down the 1/2 and drop the power by 1. So we got minus 1/2 in the power. By the chain rule, we take the derivative of 1 plus x, but that just disappears. Okay, so now we're ready to calculate what the line is. So we'll have to plug in a equal to 0 into our derivative. So if we do that, we get 1 raised to the power of minus 1/2, and we just get 1/2 out of the deal. And then 0 getting plugged in for a just gives us x. And then plugging in a into the original function gives me the square root of 1. And how about we just write 1 instead of the square root of 1? Okay, so I have my line. As soon as you have the line, you're ready to do the estimation. Okay, so we want to figure out what this number is, 1.06. I want to know what that is. So that's my function evaluated at 6 over 100, right? If I plug in 6 over 100 to my function, I get 1.06's square root. Okay, so how about we cheat for a moment and we just pull out our calculator and we say, well, what are we actually looking for? Just to get a feel for how this works. I think it's kind of satisfying that we can calculate things with our bare hands without a calculator. But if I plug that into my calculator, I get 1.02956, a bunch of other digits, but I'll stop there. Okay, now starts the estimation. So we're estimating on the line L with this same point. We're saying that, hey, it's easier to calculate stuff on this line. I don't have to deal with any square roots over here than this function. Okay, so if we plug it into the line, what do we get? It's 1/2 multiplied by 6 over 100 plus 1. Okay, so we have 6 over 200, and I can reduce that to 3 over 100, so 103 over 100, which is 1.03. Hey, that's pretty good. We got pretty close to the actual value. Of course, it's just an estimate. That's why I use the squiggly equal sign. It's not an exact amount, but 1.03, by just doing this work, applying our calculus with the linear approximation, got us pretty darn close to the real number of 1.029, pretty close to 3. All right, so the next problem is a little bit of a longer problem. Hopefully we've saved enough time to go through this as well. The curve sketching problems are always a little bit more involved, and they take some time to go through, but this is a problem that every time I've seen a calculus final exam, there's always something to do with curve sketching. It's a pretty big part of an introductory calculus class. So definitely you want to go into your exam knowing how to go through this process. So I've tried to outline for expedition all of the different details that we might need to go through. And we'll go through A, B, C, all the parts until we can finally draw our function. So just so you know, I will be able to do some question and answers afterwards. So I don't want to take time to do every single question because I know there might be lots of them out there, and I want to make sure we get through all the material. Okay, so let's start this one. I'm asked first to find the domain of my function that I'm given. I'm just noticing that this function could be simplified a bit. So instead of working with the more complicated version of it, let's try to do some simplification. I'm noticing that the top is a difference of squares. So my f of x, I can rewrite the top as x plus 2, x minus 2. And then the bottom would be the same, x minus 1, x plus 2. Okay, so that would equal, if I cross out the x plus 2's, it would equal x minus 2 over x minus 1. Now we do have to be careful with this simplification that this equal sign right here is for all x values. You plug in any x value, you get the value that's on the right-hand side, or anything that's allowable to plug into the function. But we have to kind of watch out because we made this simplification, and over here, this expression, you are allowed to plug in minus 2. But this expression, you're not allowed to plug in minus 2. So I really want to make that clear in my work that this equality here is for x values that are not equal to minus 2. Now, you can also say that x is not equal to 1, but that's clear with the picture that, okay, you can't divide by 0, so that information is carried along. But I worry that we sort of lose the information that x can also not equal minus 2. Okay, so just to expedite the process, I'm just going to shade in our values that f of x can equal in the domain on a real number line. So it can go anything towards negative infinity, but then at minus 2, we have a hole. So values, we're allowed to plug in anything there, but at minus 2, we have a point that's not in the domain. And then as we go forward, we can shade everything in up until 1. That would be another value that we can't plug in and then we can shade in everything afterwards. If you'd like to use interval notation, you can do that too. And I did that on the solutions that I posted on eClass as well. Okay, so finding intercepts. How should we do that? So x-intercepts and y-intercepts. When x is equal to 0, we'll find a y-intercept and vice versa. So first with the x-intercepts, we're looking for when f of x is equal to 0. So x minus 2 over x minus 1. We want to know when all of that is equal to 0. So that would happen when the numerator gives me 0, which is 2. And then we also want to plug in x equal to 0 and see what happens for a y-intercept. So we would get minus 2 on the top and minus 1 on the bottom when we plug it into this simpler form that I came up with. So that would give me 2. Okay, so something else we discussed in our class this semester was even versus odd functions. Now remember, with even and odd functions, there's symmetry. If you reflect over the y-axis in the even or the odd case, what you should get is either the same value or the opposite sign, right? And an even function reflects over the y-axis and gives you the exact same height or y value. And an odd function will give you the same thing but the opposite sign. So it'll give you one of those. But I worry about this point of minus 2. So it has to do this for every single value, but we have kind of this issue with minus 2 because you can plug in positive 2, but you can't plug in minus 2. So as soon as you have that situation, there's an issue that if the function was even or odd, you would get that f of minus 2 is equal to plus or minus f of 2, right? Either the minus sign here disappears, or you can pull it out in the odd case. It disappears in the even case, and you pull it out in the odd case. But neither of those situations happen, right? This one over here is undefined, and this is defined as, well, some number. You plug it into the function, and we'll get some number out of it. So they're certainly not the same thing, so I'll say they're not equal, and it's neither even nor odd. Okay, so on to asymptotes. So if we're going to look for a vertical asymptote, we want to look at every place where the denominator can be 0 and take a limit. So there's two possibilities. We're looking at minus 2 and 1, and we'll take some limits there to decide what's going on. Okay, so let's write down the limit as x approaches minus 2 of our function of x minus 2 over x minus 1. So from here, we can just go ahead and plug in minus 2, and we get minus 4 in the numerator, and we get minus 3 in the denominator. So we get 4 over 3. So from both sides, our function approaches 4 over 3 at minus 2. That means that we have a hole at this particular point, minus 2, 4 over 3. So there's not an asymptote there, it's a hole. We'll remember to draw that when it's time to sketch our curve. Okay, and the other point to worry about was 1. Okay, so we'll take the function here and write it down. And I'm noticing that we have this situation where we have 0 on the bottom and some non-zero number on the top. So that means that I'm going to get infinity out of this. I know that I'm going to get infinity. It's just a matter of whether it's plus or minus infinity. And that depends whether we approach from the left or approach from the right. So how about we approach from the left first and then try to think about this. So if I take numbers like 0.9, the bottom will be negative and the top will also be negative. So it equals positive infinity. Those two negative signs cancel out. So I'm just really thinking about the sign to decide if it's plus or minus infinity. In this case, it's positive infinity. And I'll also approach from the other side. I'll take the limit as x approaches 1 from the right-hand side of the exact same function. And now I'm going to think about values that are close to 1, but from the right-hand side, so like 1.1. When I take 1.1 and I subtract 1, this time I get a positive value. So it's positive in the denominator, still negative in the numerator, so this time I get negative infinity. So when we go to draw our function, we're going to remember that there's a hole at that point, and from the left and right of 1, we have an asymptote. On one side it goes to infinity, the other side it goes to negative infinity. Okay, so in summary, there is one vertical asymptote, and the equation of this vertical asymptote is x equal to 1. Yeah, so if I got both of my numerator and denominator as 0, then we would have to do some algebraic manipulation to cancel out what's causing the 0 over 0. And you can see that we've kind of previously done that, right? We previously did that right here. You know, if we didn't do this preliminary step, then we would have 0 over 0, and then we would just have to do that crossing out of the x plus 2 again. But I already did that to save a bit of time. Okay, so on to horizontal asymptotes. So this time we're looking for a limit as x approaches plus or minus infinity. We want to know what's going on at those extremes. And I'm going to, again, plug in my function. And from here, we just need to look at the coefficient on the largest power of x, which is quite straightforward. It's just 1. So my coefficient there is 1. So I get 1 over 1. So my final answer is 1. So there's one horizontal asymptote, and the equation of this horizontal asymptote is y equal to 1. Okay, now we're on to intervals of increase and decrease. So if you remember back to the problem, it did give us the derivative. And I noticed there's a problem on your final exam where you're asked to do something kind of like this, where you have a function and you get the derivative given to you. My point for bringing that up is that if the derivative is given, don't waste time taking the derivative, right? Because it's already given to you, and it might also be already in a nice, like, simplified form. So the idea is that we're trying to set you up to be successful here, and we are maybe testing how to take derivatives in a different problem. And here we're really focusing in on the testing of, can you apply the derivative to figure out what's going on with your curve sketch? So we did that for both the first derivative and the second derivative. So keep in mind, curve sketching, the derivative may be given to you. Okay, so in this particular scenario, there's no values that make this first derivative equal to 0. So we only have to mark down the points that are not in the domain the wholes and the asymptotes, which are these ones, and decide whether my function is increasing or decreasing in those intervals. So I'm going to try to decide if f prime is positive or negative by plugging in values into these particular intervals. And that will tell me if f is increasing or decreasing. Now, if I look at my derivative is always positive. I'm squaring in the denominator, and the whole thing is just going to come out as a positive number. So f itself is always increasing. So in this case, we don't have any maxes or mins. There's no local maxes or mins. Those just don't occur here. Okay, so find the intervals of concavity. Okay, so a similar situation here where we have the derivative given to us. There is no way to make that second derivative equal 0. So the only points that we have to worry about is minus 2 and 1 again. Those are the only points where the concavity could possibly change. So let's check if it does. So we're going to check the sign on the second derivative, and that will tell us what's going on in terms of concavity of the function itself. So if I plug in minus 1 billion here, I get negative on the top and the bottom. So that comes out as being positive. And then if I plug in, let's say I plug in 0 to this function here, I get negative 2 over negative 1. So that's positive as well. So I'll put a plus sign there. And then finally, if I plug in like 100 or something like that, then it would just be negative in the numerator. So that would be a negative result for that second derivative. So concave up, and then concave down. Okay. So in terms of points of inflection, this point here was an asymptote, so that's not a point of inflection. And this was a hole, so that's not a point of inflection either. So there are no points of inflection for this particular curve. So let's just write this down. No points of inflection. Yeah, there's no critical numbers either, right? There's no critical numbers here because minus 2 and 1 are not part of the original function. So critical numbers are numbers that are in the domain where there is no derivative of, or where the derivative is 0. So, the two ways that you get critical numbers are f prime is 0 or f prime does not exist at some point in the domain, at a point in the domain of f, and neither of these situations happen, right? There was definitely no zeros, and there's points where the derivative doesn't exist, but they're not critical numbers because they're not in the domain of f. Okay, so we're all ready to draw our curve. We can put it all together. Okay, so let's draw some important points down. First, we have a y-intercept at 2, so let's draw that in. And we have an x-intercept at 1, or no, that one was at 2 as well, 2, yeah. And we have asymptotes at 1, so there's asymptotes at both x equal to 1 and y equal to 1. Okay, and then we did have a hole. There was a hole at, where was that? That hole was at -2, 4/3. So -2, 4/3 might look something like there. -2, 4/3. And then let's remember our asymptote. It was positive infinity from the left. I'm just going to write a little dot right there to remind myself that it goes up there, and then negative infinity from the right. So I'll draw a little dot right there to remind myself that I'm going to draw it that way. And then it went to this horizontal asymptote. So we have to kind of fill in everything from here. So that's what our curve looks like, with some of the important details put down. Okay. So we're like about halfway through, onto your week 8 all the way up to 13. So another topic that we discussed was differential equations. We discussed stability and instability with both differential equations and difference equations. So I encourage you to also look at difference equations as well. Like I said, I couldn't fit every single thing into this review, but here's an example on a differential equation. And it says we're supposed to find our equilibrium points and then use a phase plot to identify their stability. Okay, so what we want to do to find the equilibrium points is set the right-hand side equal to 0. So we have f of y equal to 2 sine y minus pi equal to 0. And then it says we're going to draw a phase plot. It might be easier to just go ahead and draw that phase plot and see all of the times where our graph crosses the y-axis. Now remember, this is a y-axis versus a y prime, if you like, or dy dt. So we have like the y going horizontally and the y prime going vertically. So the y is in the usual position of where we might tend to write x more often. Okay, so it's a regular sine curve with some transformations going on here. We're doing a vertical stretch by 2 units. So instead of bouncing up and down between -1 and 1, we now bounce up and down between -2 and 2. And then we've shifted everything to the right by pi units. So sine usually looks like this, but now it's been shifted to the right by pi units. So I'm gonna go ahead and do that shift. So it's gonna start like, the bump on the bottom and then go up and down from there. And then we finally finish off at pi over 4. So it finally comes down after a full, kind of 2 cycles through its period. So I'm going to have to maybe extend my y-axis here. And this point right here will be 4 pi. Because that's where the question said that we have to stop. So it goes up and down until we hit 4 pi. And when we hit 4 pi, we return back to 0, because we have 4 pi minus pi giving us 3 pi in total. And that would be one of the points where sine would be 0. sign is 0 at every multiple of pi. Okay, and that's exactly what we're going to fill in here. So we have 3 pi, and then we got 2 pi, and then we have pi, and then 0 itself. So this equation that we came up with, I'm just going to make myself a little bit of room to write down all of the equilibrium that we came up with. So this means that y is equal to 0 and pi and 2 pi and 3 pi and 4 pi. And of course, the other part of the question is to identify the stability. So let's try to remember what the phase plot means. Okay, I was just checking my connection. Sorry, I got a warning on my screen that said that my connection was slow. So sorry if that bothered you, but if you can hear what I'm saying, then you can notice what's in the chat. Everything's all good now. So I found my equilibrium points, and I'm trying to discover if they're stable or unstable. And I was just going to say, let's remember what the phase plot means. We have y versus y prime. So y prime is telling us when y is increasing or when it's decreasing. So remember, when y prime is positive, y itself is increasing. But when y prime is negative, y itself is decreasing. So these arrows kind of help with stability versus instability. So if you started close to 0, you would end up going towards 0. If you started close to pi, you would run away from pi. So that would be unstable. And going towards 2 pi is stable, away from 3 pi is unstable, and towards 4 pi is stable. Now remember that there's stability criterion for both autonomous differential equations and for difference equations. The stability criterion is different for those two cases. So the stability criterion here would be to take the derivative, and wherever that derivative is negative, we would have a stable point of equilibrium. As opposed to the other one, the difference equation, there you were comparing your curve to the line of y equals x. So you're always asking yourself if the derivative had an absolute value of less than 1. And that's not what we're doing here. That's a different stability criterion. So I just noticed in the chat we might be getting confused with the two criterions. Okay, so here's a application style problem where we're going to be applying it to an optimization problem. So it says the rate at which photosynthesis takes place is modeled by the following function. And it says that the W represents the light intensity, and we get some number out of the deal, which makes P W as a rate of photosynthesis. So all we have to do here is apply our knowledge of trying to find a max. And it's really focusing in on what we did with the curve sketching. Look at a part of our function and try to find out where we might have this type of shape, where we would key in on a max. Where might that be? So what we can do is take a derivative and try to see where a maximum might be. So we're going to start with PW prime. So we have a quotient rule to deal with. So derivative of the numerator is 450. Copy out the denominator, so W squared plus W plus 4. And then subtract, copy the numerator, 450W. And then derivative of the denominator would be 2W plus 1. And this is all being divided by W squared plus W plus 4, all squared. And what we want to do with this derivative is set it equal to 0. We want to discover any possible points where we could have that local max. Okay, so if we set it equal to 0, we can just multiply both sides by the denominator, and there's no worries there. We don't have any zeros in the denominator to worry about, so that we can just multiply across both sides and just focus in on the numerator as the only thing that can make this equation equal 0. We can also divide out 450 on both sides. So the denominator, the 450, all of that can disappear for us. So what's left is W squared plus W plus 4 minus 2W squared minus W. Okay, so let's try to clean this up. We would have a minus W squared when we combine the W squareds. And we have a W that goes away with a minus W, so that's very nice. And then we have a plus 4. So from here, we have a difference of squares where we can write 4 minus W and 4 plus W equals 0. So we have two places where P prime is equal to 0. I'm going to again use a number line, draw it on my number line, the points of interest. We have minus 4 as one of our 2 points and 4 as the other of our 2 points. And now I'm interested in when is P prime positive and when is it negative? That will tell me what's going on with increasing and decreasing with P itself. Oh yeah, 2. Thank you. That's my mistake. Should be 2. Yeah, forgot to take the square root there. Okay, so when we plug in these values, correct that to 2 and minus 2, we would get, like plugging in minus 100, for example. This factor here, that would be positive, and this factor would be negative. So the numerator, all of this numerator here, would turn out to be negative. And the denominator is always positive, so we don't have to worry about that. So for this portion, it's negative. And then when we plug in something like 0, you would get this number here would be 2, and this number here would be 2. So the whole thing would be positive. And then at 2, it would switch back again to being negative, because we would now have a negative factor there. So that means that p is going downhill, and then after -2, it goes uphill, and then goes downhill afterwards. So we have a local max at 2. So W equal to 2 is max. And that's what the question wanted, right? It wanted to find out for what light intensity, W is the light intensity, makes PW maximal. Okay, week number 10. So here I have a indefinite integral. I'm saying indefinite because there's no numbers there. So I'm looking for an expression that is equal to this expression with, of course, no more integral sign. I want to solve that integral. Maybe something a little bit funny about this particular integral is we have an absolute value of e to the power x. However, e to the power x is always positive, right? Exponential functions are always positive. It can be very close to 0, but they will always be positive numbers. So we can drop those absolute value symbols. So e to the x is bigger than 0, so that absolute value sign can just disappear for us. So that's good. And then for the rest of it, I guess we'll have to deal with some kind of u substitution. So the standard practice is to make what's underneath the square root equal to u. So I have 2 minus x equal to u. So my du becomes minus dx. Okay, so now let's go ahead and write out our integral, trying to write it out in terms of u. So I guess I first noticed that we have an x. So what to do about this x? We could solve this equation for x. So x is equal to 2 minus u, right? If we subtract x, or so if we add x on both sides and we subtract u on both sides, then we get instead 2 minus u. And then what's underneath the square root became u. And then dx is minus du. What I'm going to do is separate this integral into 2 different integrals. So remember, you can integrate term by term. So I'm going to take my integral and apply it to the first term and apply it to the second term. Because I don't really want to do the u substitution for the e to the x part. That's fine just the way it is. So I'll write a separate integral where I can drop the absolute value signs because of what we wrote before, and deal with that one all on its own. Okay, so maybe we'll do one cleanup phase before we actually take our integral. So let's multiply in a minus u to the power of 1/2. So that would give me a u to the power of 3 over 2 minus 2u to the power 1/2. I kind of like dealing with powers instead of roots, just for taking these integrals. And then I guess we can just go ahead and take the integral of e to the x. And I suppose when we do that, we should write a plus a constant, but maybe on second thought, a constant will come out of this anyway, so we can save ourselves the trouble of writing the plus c just yet. Okay, so we'll write u to the 1 higher power, and then multiply by the reciprocal of that power. And then the other term, u to the 1 higher power, and then we multiply by the reciprocal, which is 2 over 3. So I get minus 4 over 3. And then we'd have plus e to the x. And now I'll write the plus c. And let's remember one last step here. The original question was in terms of x. So we should write our final answer in terms of x. So 2/5 and u gets put back into 2 minus x. And then 4/3, u is 2 minus x, power 3/2. And then plus e to the power x plus c. So that should be our final answer for this indefinite integral, or if you like, that should be the general antiderivative of the integrand that we started with. Okay, so we're closing in. Okay, in week 11, we talked about Riemann sums. So I gave an example of a Riemann sum on the screen here. Now, you probably won't have to do the full calculation of derivative by definition or a Riemann sum on your exam because you're just typing in the answer. But you may have a problem like one of your assignment problems from this year where you have to kind of understand what's going on with putting rectangles underneath the curve and calculating area underneath the curve. So I want to remind you of these formulas at least before we move on. So maybe there's 3 things that we need to identify. The integrand, which is this, f of x, that's going to be able to calculate the height of all of my rectangles. And then we'll have to identify the width of all the rectangles. So I'll call that change in x. So we'll do all this, maybe preamble steps in red. The change in x is b minus a divided by n. So I have 3 minus 1 divided by n, or 2 over n. And then the final thing that I need is the location of all of my rectangles. I'm going to call that x sub I. So x sub I is a plus I multiplied by the change in x. So that equals a, which is 1, plus I multiplied by 2 over n, so 2i over n. From here, we can put everything together if in our formula. So the limit as n goes to infinity to find the area of infinitely many rectangles. And we're going to add the areas together. So we'll have the sum from I equal 1 to n of the width of each rectangle, so 2 over n, multiplied by the height of each rectangle, which is f evaluated at x sub I. And x sub I is right here. So let's plug that in. F evaluated at 1 plus 2i over n. Maybe it would be nicer if I just leave this as change in x for the moment and we write another step. Okay, so we have the limit as n goes to infinity of the sum from I equal 1 to n of 2 over n, and then plugging in to our function. So it's 2 multiplied by what we're plugging in, which is 1 plus 2i over n plus 1, right? That's our function, is 2 times the something plus 1. Okay, so from here, let's do a little bit of simplifying. We have the limit as n goes to infinity of the sum of I equal 1 to n. Let's try to maybe write this out with different terms. Let's try to maybe combine the like terms. So maybe the 2 over n is fine, but then inside of the brackets, we'll maybe simplify things a bit. If we multiply the 2 in, we would have 4i over n. So that takes care of the term that has an I involved. Now let's deal with the terms that don't have an I. So we multiply the 2 in and we add 1 and we'd have 3. Okay, so from here we can use our formulas that we probably wrote on our formula sheet to deal with the sum. So I have 2 over n, right? I'm going to deal with the sum this time for n, and the I changes into the consecutive sum of integers formula, which is n multiplied by n plus 1 all divided by 2. And then for 3, we just add 3 together n times, so it changes into that. Okay, now we're ready to hopefully solve our limit. Oh, just hold on a moment. I need to adjust my brackets, I think. So yeah, we need to adjust our brackets there. Yeah, so have to be very careful. The 2 over n just got copied, and then the 4 over n got put there, and the I became that, and then there's a plus 3n, but we have to remember that that's still all being multiplied by what we had to begin with, which was this 2 over n. The 2 over n is being multiplied by all of that. Okay. Okay, now we're ready to solve our limit. And we have kind of a nice situation with our limit where we have just the ability to look at the coefficient on the largest power of n. And there's 2 terms, so each term has a largest power. So in the first term, maybe we'll just kind of save the multiplying by 2 afterwards. In this first term, we have a 4 over 2. So I'm just going to write that, just 4 over 2. That's all that breaks down this limit. Largest power on the top has a 4, largest power on the bottom, 2 multiplied by n squared. And then for the other term, all you have is a 3. Okay, so what does this work out to be? We have 2 multiplied by 2 plus 3, which is 2 times 5 or 10. Now, of course, you can check this answer by doing this integral in a faster way. So we may want to just check, just to make sure that we got the right answer, because it's pretty quick, right? We can just do the antiderivative. So if we do that antiderivative, we would get x squared plus x, and we want to evaluate that at 3 and 1. So we plug in 3, we would get 9 minus 1. And if we plug into the x part, we would get 3 minus 1. So lo and behold, we do get what we came up with below for a different reason, but you get 8 plus 2, which is also 10. So it does check out in that you got the right answer with a little bit of carefulness in the end, making sure we evaluated that limit correctly. Yeah, for limits as n goes to infinity, if you have I'll just write down a simpler scenario. If you have a limit and it's as n goes to infinity, and you have n squared plus n over n squared, you don't have to worry about this n. It doesn't, sort of play any role in the answer. The only, thing that sort of plays a role in the answer is the coefficients that you have there. So that's all I was doing. I was just looking at the coefficients that I'd have in my limit as n goes to infinity. Okay, couple more problems before I let you go for today. Okay, in this problem, we actually have to do a definite integral. And I suppose that we also need to do a u substitution here. So I would look for something to make u equal to so that its derivative appears. So the more complicated part, the denominator, that should be u. And if I make that equal to u, my du becomes minus 2x dx. So that's almost perfect because what I have in my integral here is 2x dx, and 2x dx is right there. So if I multiply both sides by a minus 1, I can go ahead and directly sub in for that 2x dx. So that's kind of nice. Okay, so my integral becomes, let's remember to change our limits of integration because my new integral is going to be in terms of u. So when I plug in 0 for x, I get 2 out of the deal. And when I plug in 1 for x, I get 2 minus 1, which is 1. Okay, then 2x dx is minus du. And then everything that's in the denominator, that just became u. So we're all ready to do our calculation here. We would get minus ln of the absolute value of u. And we want to evaluate from 1 to 2. Okay, now when we plug in 1, we just get 0 out of the deal. And when we plug in 2, we would get minus ln 2. Okay, so in the end, you just get minus a minus ln 2. So all we have is ln 2 left over. All right, one last question. Picked one of the applications for our integral chapter where we're going to calculate the area between two curves. So the two curves that we're given are 1 minus the absolute value of x and y equal to x to the power 4 minus x squared. So the curve x to the power 4 minus x squared is a little bit difficult to draw directly, so I've drawn the picture for you. Notice that both of these functions are even functions. We have even powers, so that kills negative signs. That's an even function, and the absolute value kills a negative sign. So that's also an even function. That means that we're going to have some symmetry about the y-axis. And that's kind of nice for calculating area, because we could say, okay, the area right here is the same as the area right here. They're both area A. So I'm saying that this amount in red, the red shaded area, is exactly the same amount as the purple shaded area. So how about what we do to calculate our area is just say, oh, I want 2 area. I want maybe the area A in red plus the area A in purple, calculated as twice A. So that way we only have to calculate the area for one side. And this point here, of course, is 0. We want to calculate the area from 0 to 1. You could use -1 to 0, but I prefer to work with positive numbers, so let's do that. And then we're going to do the top minus the bottom curve. Okay, so my top curve, we'll plug that in first. The top curve is 1 minus the absolute value of x. And we're dealing with just positive values of x here from 0 to 1. So we can again drop the absolute value sign. And then the bottom curve is the other one. So we'll subtract that one away. So minus x to the power 4 plus x squared. Okay, so from here we just have to calculate what this is. So we have 2 multiplied by my antiderivative of 1 is x, and then minus 1/2 x squared, and minus 1/5 x to the power 5, and plus 1/3 x to the power 3. And I want to evaluate that from 1 to 0. So luckily enough, there's kind of nice numbers here. Plug in 1, and all we get is the coefficient. So 1 minus 1/2, minus 1/5, plus 1/3. And plugging in 0, everything kindly disappears for us. Okay, so that can be now simplified to a number. I guess I'll just leave the 2 out here. And 30 looks like my common denominator. Multiply everything, your top and bottom, to get it up to 30. So I got 30, and then minus 15. And then for the 5, I multiplied by 6, so minus 6. And then for the 3, I would multiply by 10, so plus 10. And this all boils down to 19 over 15. Okay, so that's everything for the review. So thanks so much for listening and staying to the end. And I do wish you all the best for not just this final exam, but all of your final exams.